All right, so today we're looking at 6.2. It's in your Foundations of Mathematics 12 textbook. 6.2 is about 300 and let's see, what page is this out here? 384 in your textbook. In 6.1, you guys talked about a few things. We talked about degrees of polynomial functions. We talked about what polynomial functions were. We talked about straight lines. We talked about quadratics, talked about turning points, intercepts, end behavior, a little bit on domain and range. That was your 6.1 lesson. 6.2, we are going to now further our study on the characteristics and equations of polynomials. Okay, so let's get past that. Okay, so 6.2, here we go. All right, so just a few things. Let's just cover a few things. First of all, last day we talked about straight line functions, linear functions, and in your textbook they're described as y equals ax plus b, and you should know that the type of linear function that you have studied before is maybe y equals mx plus b. That should be familiar. That is the the slope y-intercept form of a straight line, and we've learned that. Probably you guys are, what, grade 12 here? You guys learned that for the last 3 or 4 years, okay? And that is a straight line. So that would be a linear function. It's a straight line. And the slope here, so if you recall, this m is the slope of the straight line. So in our look here, whatever coefficient is in front of the x multiplied by the x, whether it's positive, negative, could be a decimal, could be a fraction, a whole number, integer, whatever. That is the slope of the line, okay, for linear. Over here, this is from your textbook, right? And there's a little note here that a can't equal 0. If a equals 0, that means that this whole term is gone, and we just have y equals b. And that is also a straight line, but that's a horizontal line. If you have y equals just a regular number, that's a straight horizontal line going through that y equals whatever that number is. And I'll show you some graphs in a moment. Actually, I'll flip over here now. Let's go to Desmos, which is over here. And on the screen, you maybe can see the screen, you maybe can't see all of it on the left side here. But we have a straight line. This red line is a straight line. And over here, the format is y equals ax plus b, as in our notes. And I have a equals 1. So notice that from this point right here, 0, 0, to this point over here, 2, 2, the slope is made up of the rise between 2 points divided by the run between 2 points, right? So the rise here is 2 units, the run is 2 units. 2 divided by 2 is 1. So when we have a equals 1, we have a slope of 1. If I change this a, okay, I'm going to make this a be larger. Look what happens to the line. The slope gets larger. And so here we have a run of 2, 4 over 2. So what's 4 divided by 2? That's 2. It equals the a over here. Okay? So what about the b? What about the b value? Do you remember what in y equals mx plus b? Do you remember what the b is? Y-intercept, right. Okay, so notice right here, and let me just pause to explain this a bit more. Y equals ax plus b. I've set a to 2. I've set b to 0. So this is the same as y equals 2x plus 0. Notice that the y-intercept is 0. If I were to change the b to, let's say, 1, look what happens to this line. I'm moving the b up to 1. And so here is y equals 2x plus 1. And we have a y-intercept of 1, and we have a rise of 1, 2 over 1. So the rise of 2 divided by 1 is a slope of 2. So that should be, hopefully you remember that from years past, okay? The linear function. So a can't equal 0 there. A has to be an actual number, or else it just becomes a straight line. And maybe I should go over that too then. So what happens if we had a equals 0, like we said? Well, a equals 0, there's a equals 0. The slope is 0. It's a flat line. So if b is 1, then it's a horizontal line going through y equals 1. If b is 2, well, it's a horizontal line going through y equals 2. So that's what your horizontal lines look like. Okay, the quadratic Okay, quadratic. So the big thing about a quadratic function, and again, we're talking about something called standard form. And notice of the 3 examples I have listed here, I think you can maybe see that there's something developing here. So ax plus b, I have ax squared plus bx plus c for the quadratic. So a quadratic has 3 terms. Quadratic is degree 2, because the largest number exponent on any of the x variables there is 2. So it's degree 2. What's the shape of a quadratic? Who remembers that? Yeah, it's a parabola. So it's a parabola, which is this kind of shape here, that either opens upwards or it could open downwards, right? Well, it's a really bad parabola there, but up or down. Okay. So this a, do you remember what this a value, how this changes how the parabola looks? Anybody? If you change this number, that changes how the parabola looks. Do you remember what it does? Yeah.
I think if the a is negative, this parabola is like down.
Okay, so we have an answer over here. If a is negative, you think the parabola opens downward. So that means if a is positive, you think that it means that parabola opens upward? Absolutely correct. Very good. Anything else? Any other characteristics of this a value that maybe some of you remember from other math classes? Okay. Maybe not. Maybe not. That's okay. Let's see. So over here, I'm going to now highlight the a parabola, ax squared plus bx plus c. So I'm going to make this a value a positive number, something like a equals positive 2. So here's our parabola shape. Okay, so you're correct. If a is positive, it opens upwards. So that's a larger positive number. So here's the hint. If a gets larger, what happens to the parabola in general? It gets narrower. That's right. So if a is large, the parabola kind of squeezes in together side to side. It gets narrower. And let's test to see if a is negative, what happens? Well, we're going lower, lower, lower. A is getting to be 0. If a is 0, it is a... Oh, if a is 0, now we have just bx plus c. Interesting. So if a is 0, this x squared term is gone. It turns into a straight line. Cool. And if it's negative, there you go. It opens downward. Very good. All right. So what about this part? I'm focused on this part right now. What does this c represent? What does this c represent? And the hint is this is a constant. Notice it doesn't have an x to it. What about in this example here? What was this constant? What was this constant? That's the y-intercept. So this constant here, let's just see what happens there. Okay, so right now the c is negative 3. What's the y-intercept? Oh, gee, it's negative 3. If I move that c value to negative 2, to negative 1, to 0, to positive 1. So you can see that even for a quadratic, the c value, the constant, is the y-intercept. So let's write that down. So the y-intercept is the constant value. And yes, it's the same for our third function, which part of this just totally disappeared. This is supposed to be cubic. What's new? Hey? All these computer resources. Terrible. What color would that be? That's kind of this color, I think. Y equals ax. For a cubic function, we have degree 3 here. So this is what a cubic function looks like in standard form, cubic. And of course, the d value is also a constant. That also is the y-intercept. Okay, so recognizing the standard forms, I don't think you need to know what each a, b, and c does for each of these, really. The leading coefficient here is the a, so that's kind of important. For a cubic, if it's positive, then the cubic function kind of goes from quadrant 3 to quadrant 1 for end behavior. And if it's negative, if a is negative, then it kind of flips around the other way and it goes from quadrant 2 to 4. So that's a big thing maybe to remember for the a value for a quadratic. Sorry, cubic. Okay, now a is called the leading coefficient, and that is the number that is in front of the leading term, so it's multiplied by the x term in the leading term. The leading term carries the degree of the function. So this is the leading term here. This is the leading term here. And a term would be a collection of the number and the variable. That's the leading term here. Okay? All right, so this chart, I want to walk you through this chart. This would be very good for you to write this down in your notes. There's a lot of information here you're going to want to remember. I just happen to have these notes already made, so I'm going to show you what you should write down here. But when a is positive, that's going to be this column here. We're going to talk about what happens when a is positive. And on the right column, we're going to talk about what happens when a is negative. So it's a bit of a summary of what we've been talking about here. Okay? So for a linear function, okay, if a is positive, we know that it has a positive slope. So it's going to go up from left to right. So if a is positive for a linear function, we have a positive slope. If a is negative for a linear function, the graph exhibits, it's still linear, but it is a negative slope. And a negative slope, think about it going downhill from left to right. Negative, it's going down. Left to right is how we read, so that's a good thing to remember. Just go left to right and it's going down. Okay? So that's how a affects the linear function. We talked about this already. What happens, how does a affect quadratic? Well, if a is positive, then the parabola opens upward. And looks like a cup, up cup. Okay, here's the cup of tea. Up cup. Okay. If a is large, you said this, if a is large, it gets narrow. We saw that on Desmos just now. If a is between 0 and 1, now I didn't show you this on Desmos, but when a is greater than 1, it gets narrower. Now, when it's negative, it flips upside down. So what happens when it's really, really small? Well, I could show you that here. Let's see. So when a is really, really small, so, oh boy, this is going to be tough to, let me zoom out here. So when a is really, really small in the ax squared, or it's between 0 and 1, it's narrow. So here is a equals 1. That is sort of what we call the standard or normal sort of width. When you go between 1 and 0, oh, I got this crazy. Let's just do this here. Okay, and bring that to 0. Cool, eh? So when a is getting close to 1, look at how it flattens out. You see, it becomes very wide. Very wide. And then 1 would be there's 1, your normal width. And as a gets larger, it gets very narrow. Okay? So between 0 and 1, it's wide. All right? When a is negative, the quadratic opens downward. A large negative is still narrow. A value between 0 and negative 1, so it's a kind of a decimal, between 0 and negative 1, it's wide. And as I mentioned here before, just a minute ago, in the cubic functions, when a is positive, the end behavior goes from quadrant 3 to quadrant 1. So it kind of mimics, this like a straight line like that. Positive slope, think about that. It mimics that. When a is negative, the cubic function sort of trails downwards like this, mimicking a negative slope. Okay, any questions about that chart? Oh, you guys with me? All right. Okay. Doing good. Let's take a look at this question right here. We're almost done, I would say. But let's take a few moments though and take a look at this question. So this would be like a question from your assignment. And it says match the following functions with the graphs down here. So we should know how to do that. And you can start anywhere you want. I would like to start maybe here at h of x. Okay. Now what kind of graph is this? Yeah, it's linear. It's a straight line. What do we know about this graph? You should know two important things. It goes down, okay, it's got a negative slope. Yes. What else do I know about this? The y-intercept is negative 3. Excellent. So we've got a straight line, so it could be this one. Could be this one. Which one is it? Well, it's a negative 3 intercept here and negative 3 intercept here. That doesn't help us. They're both negative slopes, so I guess what I have to do is calculate the actual slope. Because it looks like, oh, here's another straight line equation. You see, that's got a y-intercept of negative 3. So which one would have a negative 1/2 slope and which one would have a negative 2 slope? The larger the number, the steeper the slope. So which one is h of x? Which one is h of x? Well, it's going to be the one with the not so steep slope. Okay, because the negative 2 is going to be a real steep line. See? So h of x is the 3. And how do I know for sure? Well, let's take a close look at the slope. So between the 2 points that I can see, which are the intercepts, right? I go down 1, 2, 3. I go down 3 and I go over 1, 2, 3, 4, 5, 6. So negative 3 over 6 is negative 1/2. Okay. So this one goes with this one. And obviously this q of x goes with the first one. All right? Okay. Which one's number 5? Let's do it this way. Which one is number 5 here? Well, that's a parabola. It's got a y-intercept of 1. And it opens upwards. Which one of these would be parabolas? Oh, either this one or this one. Which one has a y-intercept of positive 1? J of x or k of x? Yeah, k of x. See that? So this one right here is graph number 5. I'm having a tough time making these connections here. Okay? Getting messy. All right, so the other ones, just real quick here. This is a quadratic, opens up, has a constant of negative 2. So here opens up, y-intercept of negative 2. That's this one right down here. J of x is number 2. And then cubic with a negative leading coefficient. Well, that's going to go down from left to right. It's going to go down here like this. So this one right here, g of x, is number 6 there. Okay? And then p of x is number 4. Any questions? All right, so let's take a look at the in summary. Key ideas. I'll just highlight a couple things for you as we move through this. When a polynomial function is in standard form, so you could have equations that are not in standard form, but when they are in standard form, there's a few things you know about the graph. The maximum number of x-intercepts is equal to the degree of the function. So in a linear, there's one possible x-intercept. In a quadratic, there's 2 possible. In a cubic, there's 3 possible, and so on. The maximum number of turning points is equal to 1 less than the degree. The degree and the leading coefficient indicate the end behavior. So that's important to know, whether a is positive or negative. And the constant term is always the y-intercept, so you know that. Okay? Some things you might need to know, and I won't spend too much time on this if you've read this, but linear and cubic polynomial functions with positive leading coefficients have similar behavior. So I even drew this just on this diagram, maybe up here. that you can no longer see. But the graph right here, so cubic, right, kind of mimics the linear. So the end behavior would be the same for those odd functions. So really linear, degree 1, cubic, degree 3, was it quintic, degree 5, and so on, 7, 9. Those are the end behaviors are the same. All right. Okay, so there's your assignment you guys are working on today, and that is the lesson for 6.2. Okay, so here's just a copy of the textbook in case you need to see these questions. 6.2.